Hello. Yes, it's working. Welcome to today's webinar. I think we're having technical difficulties with the Dyalog TV chat. So I'm going to ask right now, if you want to ask questions during this webinar, that you go to, and I think I can show you this on here, go to the Apple Orchard Stack Exchange chat room. If you have a Stack Exchange account, then you'll be able to ask questions in there, and Adam is in there and he'll relay those questions to me. You can find it by searching on the internet for APL Orchard, APL Orchard, and you should find a link like this. So, other than that, let's get started. I'm going to be giving a very surface, shallow look, quite quickly, at an overview of what is ultimately a really broad, vast and deep topic, which we'll explore in more detail in the future, and that is fast APL. So that's high performance APL code, or optimizing your existing code, or writing high performance code, either way. And the audience for this is generally going to be APLers, people writing the APL code, even though there is a lot of content, a lot of media that exists about implementing interpreters that perform well, and things like compiling APL is a whole field of research. And some of that information is useful for APLers, so where it's relevant, we'll address it. But in general, this is for APLers. To give a bit of context, I want to talk about goals for code, and APL in particular. One of the main advantages from my perspective is the ability to express ideas in APL. And it's great, and it kind of mirrors natural language in the sense that there are, and this is true for other programming languages as well, there's multiple ways to express similar ideas or even the exact same idea. But the way that APL primitives and the functions and operators, the way they compose together, and the syntax of APL, the terseness as well, I think makes this particular facet of APL quite pronounced. So you have this double-edged sword where on the one hand it's quite fun to be able to express your idea in kind of the first way that pops into your head, and it doesn't take too long to try things out. You can also play with different ways of expressing similar things. But on the other hand, especially in production code, sometimes you get this nagging feeling like, is there a better way to do this? What's the best way to express my idea? And then you start getting into the whole thing about what is good code really. Aaron Su and Roger Huey offer two perspectives. Aaron asks, how much are you willing to bet that this code does what you think it does? That it's going to accurately reflect your idea. And Roger Huey has coined the term monument quality code, which is like this kind of ideal of code that maybe could stand the test of time, or it's really good. But these are both quite broad statements, fairly lofty and high concept. Roger's has this aspect of maybe aesthetic beauty tied in there, so like literally beautiful to look at code, whereas Aaron's is a bit more pragmatic. He's kind of asking, how much are you going to bet that this code does what you say? But both of them come with this assumption that your code is accurate, that it does, it performs the correct computation, and that it's reliable. It will do this over and over and give you the right results. So those are your non-negotiable things. Your code has to be accurate and reliable. But when it comes to writing code, there are other things that you have a bit more control over, in a sense, or things that you're going to be trading, balancing between. Adam Brzezinski has addressed this in a previous webinar on code golf. So he was focusing on short code, but the context really here, or the idea of better code here is partially readability. Can someone else come in and look at your code, understand what it's doing, and be able to maintain it into the future. And fast, which is obviously what we're focusing on here. And shortness kind of ties into readability in some sense. You know, there's a sense in which shorter code is more readable just because there's less for you to pass. But also, if you go too far, then you end up, you know, you're using weird tricks that are harder to read. So there's a balance there. And in general, in production code, you're going to want, I think, mostly readable, you know, maintainable code. But sometimes there are going to be parts of your code that you need to perform well. And that's when you're going to consider doing whatever you can to make sure your code performs reasonably and is fast. And that's obviously a whole thing in itself, which is why I'm doing this introduction right now. I've broken down this topic into these sort of vague subtopics where they're mostly from the perspective of, you know, code you've already written the solution and it works and it's accurate and reliable, but maybe, you know, it's not quite as performant as you're hoping. But a lot of the advice will also obviously apply when you're going into the future and you're working on a new project and you know that part of the code, you know, for part of the code performance is critical, then some of this advice is going to be really valuable then as well. So when it comes to, I don't know, comparing different bits of code, different ways of expressing the same code, or, you know, analyzing code you've already written, then obviously the analysis and profiling tools that Dyalog provides are going to be important. And through those, you're going to identify hotspots, which are usually single lines of code which are causing your poor performance, and you might want to, you know, do something to address those individual lines. And you know, there are these things we're going to look at, like mechanical sympathy, being aware of the special cases and the things the interpreter does under the hood to make sure your code can perform better than you might expect if you naively coded it in some other lower level language, for example. Compilation, as I mentioned, is a whole field of research. And then I'm only going to mention this right now. I think I've heard it phrased before, and it kind of relates, that sometimes the best solution to a problem is to not have the problem, and you get part of the way to that through outsourcing jobs. So if you are just you have this thing, you already know there's a library out there that's high performance and it gets, you know, does what you want, then just use quad NA and, you know, call out from APL to that library to do that particular bit of computation. That's all I'll say about that. And finally, there's this sort of category which is algorithmic complexity, and this is related to, you know, what's known as big O notation. So, how does the performance of your algorithm change as a function of the input size? And for us, the input size is going to be the number of elements, so the product of the shape of your array, usually, especially for high performance. So I'm going to look at a couple of very trivial examples to show you the profiling tools to start with. But before that, I want to address the first rule of fast APL, which is that you should not try to optimize code which isn't proving to be slow in realistic situations. This is partially because the optimized versions of your code are quite likely to be longer, harder to maintain, harder to see exactly what's going on because you're doing special things to make sure it's fast. And more importantly, it's just a waste of time if it's not actually going to benefit you to put in the effort to optimize your code. So that's the first rule. To look at profiling, as an example of that of code that's unnecessarily optimized, I want to show you these two versions of life. Right, so life is a very typical APL example. Here we have our nested array version, which is very similar to that shown in the famous John Scholes video. What you get here is 9 nested copies of your array, sort of showing all the neighborhoods in the 3x3 space. and then you do some computations on those. The second version here is the same computation, but it uses rank so that we can keep the arrays flat the whole time. There's also a ravel with axis in here. The whole thing is longer. If you're not that comfortable with rank, that's going to be a whole thing. I mean, it is much less readable, but worse than that is the gains are just not really that good. For a 27% speed up for that sacrifice in readability, it's just not worth it. So, and since there's only 9 copies of your array in the nested version, as your array scales, your gains are going to be even more negligible. So there you go. What you saw a second ago was the runtime user command, and that allows you to both see the amount of time an expression is taking, but also compare multiple expression timings. And it's basically a wrapper for the def and cmpx function with a couple of extra things. These are fairly well documented, so I'm not going to go into loads of detail on how to use these. Profile is slightly different. It also does expression timings, but it can also show you the breakdown of a multi-line function and how much each line is being called and how much CPU time each line is taking. So to show you that, I'm going to look at 2 codings of the mean average function. Pretty typical APL expression, especially when you're showing trains off. But here I've parenthesized these 2 equivalent expressions to show you the difference in how they'd be computed. So in the first one, this is kind of the typical way of doing it. You count the elements to find big N, then you sum the elements up, and then you do that sum single number divided by a count single number, so you just do 1 division. In this version, it's mathematically equivalent and you get the same result. But here, okay, you count for a big N again, but then you're dividing the entire array by big N, and then you end up, well, if our array is integer, then you end up with a bunch of floating point numbers, and then you're summing floating point numbers. So you get hit twice in this version. As you can see, the performance of the second version is much worse. This is just simple CMPX, and we have N as 1,000 integers. With profile, it allows us to break it down into lines. So this is how you use profiling. If you're doing it multiple times, you're going to want to clear the profiler. Then you start the profiler, then run all the functions that you want to test, then stop the profiler, and then you can use the profile user command, which on Windows, it pops up a nice GUI. If there's multiple functions, then you can get a pie chart, which is quite nice. On other platforms and on the Jupyter notebooks here, actually Jupyter on Windows also pops up, but on other platforms you get this text output. And here it's broken down. You can see how what percentage of CPU time is spent on each line. But because the expression is so short anyway, we don't have enough resolution to see the millisecond timing for one call. So what I've got here is a sort of simple operator which does all the quad profile stuff, but also allows me to run the function a certain number of times. So I'm going to run my functions 10,000 times to compare them. So for our first one, you can really see the difference here. Most of our time is spent summing up with our integer summation here. And that's taking 11 milliseconds for 10,000 calls. And the division takes not very much time at all because it's 2 integers being divided together. In our second version, we're now spending a lot more time on 2 of the lines. One is dividing the entire array, which is line 2, and another one is summing up a bunch of floating point numbers, which takes much longer. So overall, this version's much worse. But that's how profiling works. And that can allow you to dig into your functions to see how their performance is. That specific example is sort of partially tied to mechanical sympathy, but I think it's mostly about algorithms and how you're implementing a certain computation. But the phrase mechanical sympathy, I've started using it since Martin Thompson came to the Dyalog 18 user meeting, and he was talking about advances in modern hardware, things like CPUs which can sort of use common memory access patterns to read memory ahead of the computation you're actually asking for, and that can produce big speed ups, all kinds of clever things, and you can see the talk on YouTube. But really, I mean, the phrase is kind of self-explanatory. You're considering what the computer's actually doing, and how that's going to affect your computation. So it's kind of unfortunate that a big part of APL is that numbers are numbers and characters are characters, and you don't have to worry about what the computer's doing. But obviously, if you want high performance, you're going to have to care about what the computer is doing. So that's what mechanical sympathy is all about. But it does allow you for relatively easy gains if, especially for single line hotspots, you can get some decent performance gains from things like not using nested arrays or mixed type arrays. The reason for that being that internally, this is sort of rough model of how it works. Inside the computer in memory, an array is stored as its shape and then the ravel of arguments all together in memory for a flat array. And so picking out a chunk of that memory, especially if it's all contiguous sequential access, then that's really quite quick. And even if it's, say, going down the columns and it's a regular pattern, that can also be relatively fast on modern hardware. However, if you're using a nested or a mixed type array, and this example is both, then you have your shape, and then you have a bunch of pointers, and they're pointing to other arrays which consist of a shape and then a ravel of arguments. And so even if you're indexing consecutive items in a nested array, the poor computer has to go following this trail of pointers to grab the data that you actually want to use, and you'll incur a big penalty for that. So as an example, from when I was doing physics simulation stuff, I wanted to find the sort of distance matrix between a set of points. So we have 5 points in 3D space here. Our first representation is a nested vector, 5 3-element vectors, and our second representation is as a matrix. And you can see that the naive coding of my distance, so we have Euclidean distance, the square root of the sum of squares, but the main bottleneck is our outer product subtraction. And in the nested array case, it is about 14 times faster to use flat arrays. Or rather, it's 14 times slower to use nested arrays, sorry. And we have this table operator, which is using multiple ranks to do the same computation. And ultimately, it's much faster for not really that much effort. You can see the same technique of multiple ranks to do a kind of outer product was applied in the life example a moment ago. There are other aspects or other things you can dive into, and we probably will in the future, related to this idea of avoiding nested arrays or using flat arrays where possible. These include using inverted tables, and Roger Huey has a talk from Dyalog 18 there. There's also the idea that, if possible, try to do work on the largest array that you can for the job you're doing. So in this disastrous example, it's kind of related to the life example again. We're taking 3x3 neighborhoods in a Boolean matrix, and for each of those neighborhoods, we're adding up the elements. So it's the count of ones in a neighborhood, and are there more than 3 ones in a 3x3 neighborhood, and do that all the way around our big array. And you can see in our sort of naive coding, but it's slightly nicer in a sense. You're saying for each neighborhood, sum up the elements and tell me if it's greater than 3. So it kind of makes sense when you read it out loud like that. However, as you can see, if you count the neighbours first, I mean, on top of that, I think this is also special cased in the interpreter. So the interpreter recognises this bit and performs fast. Although this might be similar. But you get that whole result of sums of neighbours as a single big array, and then do your comparison afterwards, and you can see you get a massive speed up for quite a small change in the actual code. So there we have what we're calling the interpretive advantage, and that is, even though typically you consider compiled languages to be faster, I mean, it's a lot. The interpretive advantage is the interpreter implementers put a lot of work in to making sure that all kinds of different cases run relatively quickly. So this includes certain phrases which are recognized, and such as this, a special case of key, which is much faster. But also the Dyalog idioms, I think, come under this category. And so that's a whole other topic that you can explore, that we will explore, which is you as an APLer being made aware of all of what's available in terms of interpreter tricks that you can utilize to make sure your code is working reasonably, is being reasonably performant. So here's an example of the sorting idiom. On the left is the sorting idiom, and on the right is the same sorting algorithm, but it's not recognized by the interpreter. There's also another little trick. If you're not using floating point numbers, it might be prudent to use quad CT get 0. So then you're not incurring, extra computation of tolerant comparison. If you don't need it, then don't use it. It's a waste of computation. And then, so that brings us to, but not really that smoothly, the sort of category of algorithmic complexity and how that ties into the APL primitives. And there's a discussion about this in Aaron Su's PhD thesis. But also the point I want to make just for this video is to say, I mean, in other languages, because you're going into the details of the implementation and sort of at the fine grain level, having to write these loops out, and maybe it's loops with conditionals. So, for example, it makes it slightly more difficult to reason about the algorithmic complexity, right? The computational complexity class of your algorithm. How much is the performance going to suffer for a large input size? So for example, you can have a for loop, and that's basically linear with input size. You can have a nested for loop, and then it becomes n squared. But if you have something complicated with, conditionals mixed in there, if statements and such, branching, then it becomes more and more difficult to reason about your algorithm. But because APL consists of these well-defined primitive functions that compose in very regular ways, it's relatively more easy to reason about your algorithms in a technical way. So as a not very good introduction to big O notation, it's basically saying, and we'll just focus on the time complexity for this sort of brief overview here. For my function, my algorithm, how much time will it take if my input is n elements long? And for addition on sort of a Turing, a ticker tape Turing machine type thing, you can get sort of linear time, so it scales linearly with the size of your input. Mod is somewhere similar. Outer product is kind of this nested for loop idea. It's inherently n squared usually. And so if you learn the complexity class of all the APL primitives, because of the way that they compose, you're basically just adding up these big O's. And the way that it works is for your asymptotic complexity, which is, as n goes towards infinity, what's the behavior like? Then your larger terms dominate, and so for example, if you had, something plus something mod something dot f something, it's this outer product, this n squared bit, which will dominate as n tends towards infinity, and you can neglect all the smaller terms when you're doing a sort of broad strokes analysis of your algorithm. So I'm going to do a very, very brief look at this sort of example. It's 4 functions which compute prime numbers from integer primes from 1 to omega. PT0, our first version here, is kind of it's a nice thing to use when you're introducing APL to people. It's quite a traditional approach to doing it, using comparisons and reduction and an outer product, and in division remainder, the modulo function. But we have this outer product, and okay, if we look, so iota, I think iota's basically linear in omega. Your outer product is n squared. Comparison is linear in the size of omega. Your plus reductions linear in the size of omega. Another comparison and where are also linear. So for large input sizes, ultimately your outer product dominates massively, and you have an n squared algorithm. It doesn't perform very well for large input sizes. Similarly, we have another n squared algorithm, but instead of modulo, we're using multiplication, which is simpler, so we should get a smaller factor on that n squared. Then these last two, PT2 and PT3, we have the sieve of Eratosthenes, the Diefen's version, and PCO from Diefen's, which for the most part is basically a lookup table. So it should be order 1 or constant time, but I think there's a large overhead. It's quite a substantial function. Very briefly looking at the sieve before I'm going to show you comparison of these as graphs, a comparison of all these functions. For the sieve, you can see we're going to be interested in this line because it has a recursion, so that automatically adds some complexity. For the most part, what's kind of interesting here, and I think we'll go into more detail in a future video, is the left expression in our recursion is catenation, which is linear in the size of alpha, but every time this function recurses, alpha increases at most by 1 element, right? Because next is just the 1 take of omega. On the right hand side, we have a mask and a compression, which is linear in the size of omega. However, on each iteration, that size decreases quite dramatically. So, and you've also got, so it's linear in the size of omega, but also that means it depends on the distribution of primes, as the integers increase. And that distribution has a logarithmic aspect to it. So we have order of n from the recursion and log n from our filtering. This guard stops the whole algorithm short, but the amount that it stops short also depends on the distribution of primes as the integers increase. And so that adds an extra logarithm factor in there. So we have log n, and our linear concatenation of alpha is just n. So I think ultimately that's a reasonable way of getting to n log n. But we'll go into more detail in the future. I want to expedite this so I don't go to an hour and 10 minutes again, here's a simple timing, another simple timing operator, which I'll use to compare all of those prime number functions. So copy sharp plot in. Here's a plotting function. I won't show it for long. It's not that interesting. But here we are. Here are graphs of our performance. So we have these input sizes. These are our big N's, or little n's a moment ago. And what you can see is that our modulo reduction, basically as expected, looks pretty well quadratic to my eye, but again, we're doing a very, we're doing a not very detailed analysis right here. And also I haven't done the necessary steps to make sure these are very accurate timings. We also have our multiplication version, which is also quadratic, but the factor is generally smaller because multiplication isn't quite as complex as the modulo reduction. This line here is our sieve from Diefen's, the sieve of Eratosthenes, and you could argue there's a kind of log thing going on here, a logarithm pattern. And at the top we have Diefen's PCO, which is very flat, on the whole, except there's clearly this big overhead from loading the big function in the lookup table. So the exciting thing is as we move to the right, now we can see something. I apologize if this is quite hard to read. I should make the lines thicker. When I publish this, it's a Jupyter notebook. When I publish it, I'll change the plot function to make the lines thicker. Although I guess at that point you won't need it. So we have the same pattern from our previous graph, and we expect modulo reduction to be consistently worse than our multiplication one, but we get this sudden giant leap here, which is kind of curious. But it turns out that it's because where mod will sort of always produce smaller numbers even as the size increases, mod will always produce smaller numbers as n increases compared to multiplication. Even though multiplication is simpler, as n increases, an outer product multiplication table is going to end up with huge numbers quite quickly, and eventually we reach the floating point regime and our performance suffers massively. So this bit really ties back to that first rule of fast APL, which is if your code isn't being slow in realistic situations, so in this example we could imagine a realistic situation being that we only ever compute in this low n regime, our n squared algorithms are actually faster because there's much less overhead and all our optimizations were for nothing. But of course, if you're up here, then you're going to be contemplating the sieve or PCO, and I imagine if you keep going further up, PCO is going to stay relatively flat up to a point. Depends how big the lookup table is. So that's a very small taster of that part of analysis of code. There's also, as I mentioned, compiling pieces of code, and so there's been research about compiling APL since APL was a thing, but I think the modern consensus is you want to have mostly interpreted APL with certain parts of your code compiled, and that's sort of been the focus of these three projects. There's Aaron Su's CodeDefense compiler, Jay's Dyalog compiler, which you can find in the Dyalog help, Robert Benecki's APL parallel executor, and these I hope to explore more in the future. Yes, that is my brief whistle-stop tour overview. You can see it's such a vast topic that in over half an hour you've learnt probably almost nothing. But in the future, we're going to be addressing these topics in more detail. Some maybe webinars, maybe other videos. For now, that's the sort of introduction to Fast APL for now. The next webinar will be next month on Thursday the 19th. I'm going to assume from my lack of response on here that no one's been saying much in the orchard, and I apologise for the technical difficulties on Dyalog TV. Next month I will be exploring progressive set functions, so that will have a bit more meaty explanation. It's quite an old topic, but there's plenty of stuff there that's kind of interesting to talk about. So this is things like index of dyadic iota, epsilon, the membership function, union, intersection, the set functions. There is a category called progressive set functions, which are progressive versions. I will explain what all this means next month. Is there anything else? I think that's it. So thank you for watching. Yes, and this is very much just a taster of things to come in the future. As I said, it's a crazy vast topic, but I think it's very interesting. And there's sort of lots of information that's sort of spread out all across, documentation and internet articles and videos. And the aim for this sort of project series of videos and articles is going to be to collate a lot of that information so that it's easier to digest for APLers. All right. Thanks very much.